Hey Adventers, welcome back to our Advent of Code journey. And today we are going to solve day 14. And speaking of 14, you can see I'm presenting to you today from a tetradecagon camera. That's right, a tetradecagon is a 14-sided polygon. And here's a little trivia for you. When do you think the face cam around me will start resembling a full circle? Let me know in the comments below. And yeah, if you're new here, welcome. I'm Jatin Kumar Malik. I'm a principal engineer who absolutely loves solving these puzzles. And if you have missed the last few videos, you can check my day 1 to day 13 playlist here, where we go behind the scenes to solve the problems without spoiling any solutions. And trust me, that's a great way, even if you are a software engineer or if you are someone who just like puzzles, it's a great way to understand and discover some of the new techniques of problem solving. For example, yesterday, the day 13, we got a chance to dive deep into the world of linear algebra. And I think I did that after like a whole decade and I got to learn something new. So yeah, check that out. And let's begin. So today we are again at day 14. So let's get started. So day 14 problem today is called Restroom Redoubt. So one of the historians need to use the bathroom. Fortunately, there is a bathroom near an unvisited location on their list. And so you are all quickly teleported directly to the lobby of Easter Bunny headquarters. I recognize that. Unfortunately, EBHQ, Easter Bunny headquarters, seems to have improved bathroom security again after your last visit. Yeah, I knew it. Oh, so this is a reference to 2016, I think back to the origins of Advent of Code. And the area outside the bathroom is swarming with robots. To get the historians safely to the bathroom, you will need to find a way to predict where the robots will be in the future. Fortunately, they all seem to be moving on the tile floor in a predictable straight line. So we have a bunch of robots who travel in a straight line. Okay. And you make a list, that is your puzzle input, of all the robot's current positions, P. So robot has a position P and a velocity V. One robot per line, for example. So we are given an example here. Before I write that, so it seems like we have a position X, Y, and we have a velocity maybe A, P. It can be anything. And let me get this example here so we can talk about this more in detail. Perfect. So let's read on the question. It says that each robot position is given as P is equal to X, Y, where X represents the number of tiles robot is from the left wall and Y represents the number of tiles from the top wall when viewed from the above. So a position of P 0, 0 means that robot is all the way in the top left corner. So the room or the puzzle input that we are given resembles something like this. Let me get the edges all right. And what we are given is that this starts at 0, 0, and maybe it is an M, N grid, like on which the robots are walking outside. And the robots always starts from here, the P that is given here, which is their initial position. So in this example, if I had to see, so 0, 1, 2, 3, 4, 5, 6. So let's say this is 6 and 0, 1, 2, 3, 4, 5, 6, 7. So then this becomes 6, 7. We can see that if we look at this example here, our robo is at 0, 4. So 0, 4. So this is the starting position. Let's say we call it R. And then you have a velocity of V3, minus 3. Let's see what that means. So each robot's velocity is given as V is equal to XY, where X and Y are given in tiles per second. I see. So this is per second, and this was our initial position. So what that means is that positive X means that robot is moving to the right and positive Y means that robot is moving down. So a velocity of V1, minus 2 means that with each second, which is our time interval, the robots move one tile to the right and two tiles up. So the robots outside the actual bathroom are in a space which is 101 wide and 103 tiles tall. So we are given like our puzzle input that is given to us. That is a grid of 101, 103, which is nothing but basically this thing that I made here. And however, in this example, the robots are in a space which is only 11 tiles wide and 7 tiles tall. So this example that is given, it is given like that. And if you have to see this one, so in this we can see that our robot is moving, if it is starting from 0,4, it is moving 3 steps to the right and minus 3 steps to the above, which seems like it is going out of bound, but let's read on. So the robots are good at navigating over and under each other due to a combination of springs, extendable legs, and quadcopters. Interesting. So they can share the same tile and don't interact with each other. Visually, the number of robots in each tile in this example looks like this. So let me copy this and paste it here. So this is the visual representation of the robots that are given us here. So this is represented like this. And remember, this is that T0, the initial starting position. And what we know about robots are that they have an initial position and they don't collide with each other. So collision is not something that we need to look at. And these robots have a unique feature for maximum bathroom security, that they can teleport. That makes sense. When a robot would run into the edge of the space they are in, they instead teleport to the other side, effectively wrapping around the edges. So what they are saying is that it can teleport, which is a fancy way of saying that they will wrap around back to the other side. And how that works, we are given an example here. So here is a robot at P 2,4, which is the initial position, and V2 minus 3 does on the first few seconds. So let's try to simulate that. So that I'll make some space here. Let's make it like this. And this is our robot. And let's use some color coding. So for white, let's say this is the position that represents T, 0. And this robot that we are given has a velocity of 2, minus 3. So that's the velocity. And this is the initial position that is given. So they have explained how it goes in first few seconds. So let's try to dry run it ourselves and then compare notes. So that is very important. A lot of times, like once you understand what a question is doing a dry run with a test case is a very interesting way to quickly understand the question and just confirm what you're doing is correct. So let's see what would happen at T1. So T1 is basically after 1 second has passed. So the velocity is 2, minus 3. So minus, remember, is going up and positive is going here. So we can see that after one position, it will go 1, 2 here and 1, 2, 3. So this will be the position of my robot right here. And yeah, we are not given any name or anything for robot. So this one is currently, let's say, representing that, but we are going to represent this with this dot. So this is T1. So let's see what happens after 2 seconds has passed. So it will go 2 steps to the left. So it will come here and minus 3. So 1, and then it will do a wrap around 2 and 3. So this is where it should land after 2 seconds have passed. And we can confirm that after 1 second, it was here. And after 2 seconds, it is here, which looks correct. And let's do one more dry run using color blue. And we say like at 3rd second, this robot again move 2 steps to the right and 1, 2, 3 steps to the up side. And then it lands here, which is our 0, 1, 2, 3, 4, 5, 6, 7, 8, 0, 1, 2. So 8, 2. And then if we have to do one more dry run with the orange color, T4, we can see again it will shift 1, 2 steps here and then 1, 2, 3 steps here. So this should land in the corner after T4, which is correct. And then so on. We are given another after 5 seconds where now for here it was wrapping around like here. And if I take one more color, it will now wrap around both here and here, which means it should land 1, 2. So 1, 2, 1, 2, 3. So it should land somewhere here, which is the T5 again. So this is pretty clear. It's an interesting question. And already I can think of some of the ideas, but let's read on. What do we want to get as our answer? So it says that the historians can't wait much longer So you don't have to simulate the robots for very long. Where will the robots be after 100 seconds? And this gives me flashbacks to the yesterday puzzle where also we had a similar constraint of 100 turns. But let's write that. So we are saying that we are more interested in finding this dot 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 dot. And if I have to write here, we are more interested in finding T100 position for all robots that are in our input. And for in the above example, the number of robots on each tile after 100 seconds has elapsed looks like this. So remember we were given an example above. So let's make some space. This is the position after 100 seconds has passed, and this is mentioning for this input here. This is how it looks like. And let's see what we have to do now. So to determine the safest area, count the number of robots in each quadrant after 100 seconds. Robots that are exactly in the middle, horizontally or vertically, don't count as being in any quadrant, basically, which are on the boundary. So the only relevant robots are this. So what we have done is we have divided this quadrant into two parts, something like this. And if I have to draw another line from here, something like this. And what it means is that all the part numbers that comes on the line, so like this one, this one, this one, they don't count at all. And in this example, the quadrants contain 1, 3, 4, and 1 robots. So how does that work? So this is 1. This is 1, 2, 3. This is 1. And this is 2. So I have a feeling because it mentioned that these robots don't collide, there is a very high possibility that there is possibly this is 3 and this is 4, because that was the order 1, 3, 4, 1. So there is a chance that there is some kind of an overlap on one of these values, and similarly here also there is an overlap, which is fair enough. And this also gives us a hint on when you want to write code, how would you want to represent these positions. But okay, so we have 1, 3, 4, 1. What do we have to do? So multiplying these together give us a total safety factor of 12. So there is something called a safety factor. And that comes around 1 into 3 into 4 into 1, which comes around 12. Is that our answer? So it is asking us that you have to predict the motion of the robots in your list within the space which is 101 tiles wide and 103 tiles tall. What will be the safety factor after exactly 100 seconds have elapsed? Interesting. So the question is fairly clear that we will have a grid of 101 cross 103. We have to find the T100th position of all the robots. Once we find that, we have to draw these lines, that quadrants, and then we have to calculate how many robots fall in each quadrant, and then we have to multiply. And the order doesn't really matter because you're multiplying, so it doesn't matter how you count the quadrants, but it has to be 4 quadrants. And once we get that, that should give us our answer. So the problem is fairly clear, and I hope it is fairly clear to you as well. So I think now is a good time for you to pause and think about how you would solve these problems and what is the initial approach that you will take. And pausing now and thinking will allow you to come up with one approach, and you can be very creative. I already can think of 3 to 4 ideas here of doing that. But think about it, have an approach, and then when I come back, we are going to compare our notes and we are going to see like what approach am I planning to take and write code to solve that. So yeah, pause now and I'll be back in just a few seconds. So yeah, if you're ready, let's talk about some of the initial approach I can think of. So I will use the trusty orange color to talk about hints. I think one of the first thing that is very important in this question is that how would you do the representation of these robots? And remember, when you have a robot, you need to store 2 things. You need to store position and you need to store velocity. Does that give you any idea? And hint number 2 is here that how would you store and update their positions at every t interval, which is 1 second in the question, because you have to kind of simulate till t100 seconds. And if you're thinking something around a 2D array, while that may work because you can create a grid of 101 into 103, there is one interesting caveat, because remember, there is a case where the robots can overlap. So using a grid as your source of truth for the positions, you will need to be very careful about how you are storing, and that you don't make a mistake of, instead of overlapping, don't make a mistake of overwriting a robot with another robot. Because remember, the robots can go around each other on the same position without affecting anything about their movement. So I hope that helps. So in this case, what I'm thinking is that having a 2D array is not required at all. All you need to care about is this thing here, where you just want to store this. So I think here object-oriented programming comes into my head, where I can basically just create these objects. And then when I run my main loop for 100 seconds, all I need to do is that at each iteration, I just need to update the position. And when I update the position, the second most important thing that comes into the picture is, like in terms of constraint, is our grid size that is given to us. And grid size is 101 into 103, which means you will need to understand a way on how would you handle the out of bound scenario. An out of bound scenario is conveniently called teleportation in this question. So how would you do teleport? So if you have done like any of the problems, similar problems, you already know the answer, that you can use the modulus operator. So how modulus operator works is, let's take a small example where you have a grid of 4 sizes where the indexes are 0, 1, 2, 3. And you are playing the same thing where you want this teleport thing to happen. And this reminds me of a classic Snake game. Like if you ever had any Nokia handset, in the Snake game, there used to be 2 modes, where there used to be like a classic mode and there used to be like some kind of an infinity mode. So in the classic mode, when you were playing Snake and you were chasing the food, like you were not allowed to go through the wall. But I remember there was this infinite mode or some creative mode where, like, when you go through here, you would come around here. And if you go through this wall, you would come back from this wall. And this is exactly same, like if you have done that. So how that works is, like, you use modulus operator, and modulus operator has a property where it can give you the remainder of, like, whenever you do a division. And if the number is smaller than the divisor, it just gives you the same value back. So for an example, if we have 4 positions here, and if my robot is here on the first position, so 1 modulus 4 will give me 1 back, because it's less than 4. And 4 modulus 4 will give us back 0, which means, like, anytime I go beyond the 3, it resets my position to that. And to see that, what I can do is I can check 6 modulus 4. So let's say if I was at 1 position and my velocity is that I have to go 5 steps ahead in x direction, since this is a 1-dimensional array. So it will go something like this, where it will go 1, 2, it will come back here 3, 4, 5. The answer should be 2. And if you try to do 6 modulus 4, your answer will come 2. Because in a total span of 4, when you do a modulus, you get back the remainder of the question. And using this same approach, you will basically have to calculate the modulus in both the directions. So remember, you can go in all 4 directions in a grid based on your x and y positions that are given in the velocity of the robot. That is here. So whenever you move on a per second inside this loop, you will have to calculate the x and y position of the robots and update these objects. And the idea is the quadrant part also sounds confusing and may want you to create a 2D grid, but you don't actually need that, because in 3, after t100, like 100 seconds have passed, all you need to do is you need to iterate over the list of robots, like no matter how many robots are given, and you need to find out the bounds between a grid of, so if you have a grid that is 101, 103, you just need to find the middle element. And then for the value, this value of x and this value of y, you just have to ignore all the robots that falls on the line. And then you can calculate which falls in which quadrant. And once you get that, you just need to do a product of that, and that should be your answer. So I hope this explanation helped you. What I'm going to do is now I'm going to go ahead and write some code so that we can quickly get the answer of our part 1, and we can move to part 2 where all our hopes and dreams will be crushed when this 100 seconds limit will be removed. I know, I'm foreshadowing based on my experience from last few days, but yeah. So I would also suggest you to jump into your codepad and write some code. Don't be afraid of experimenting. And even if you want to go ahead with 2D array, what you can do is that each element or each cell of your 2D array, you can design it in such a way that it can have multiple robots. And in that case, you should be golden and you should be able to use that. And you can then draw these interesting visualizations as well. But with that, I'll go and write some code, and so should you. All the best. And hey folks, welcome back. As you can see, we have solved the first part of day 14. And talking about my approach, I followed the exact same discussion that we had above. I just ran a loop and I maintained a record for all the robots position, and after 100th position, I just calculated the midway for both and did that. I made a rookie mistake when I was calculating the mid X and mid Y, where I just did a single division by 2. And the problem is that for 101 and 103, it ended up giving me 50.5, and here it ended up giving me 51.5. But I was able to add a debug point, and I was able to soon replace it with double division in Python, which instead of giving a float gives you a seal number. So that was correct, which was 51 and 52 for this one. And we were able to find the 51st and 52 position, and then we were able to find the quadrants, multiply them, and get the answer. With that, I think it's time to move on to part 2 and see what it holds for us. So I'll make some space here. I'll add part 2, and let's read it. Oh man, it's one of those. So part 2 is in the bottom. I always look up here, assuming that it will be a lot. Don't worry about the answer. I will hide that. It says that during the bathroom break, someone notices that these robots seem awfully similar to the one built and used at North Pole. If they are the same type of robots, they should have a hard-coded Easter egg very rarely. Most of the robots should arrange themselves into a picture of Christmas tree. Okay. So we are going in positions. So here we went for the 100 times. It is saying that very rarely, like the grid that we saw, the robots should align them in some kind of a shape of a Christmas tree. But what does that mean? Where is the Christmas tree? Like we are not given. There are multiple ways of making a Christmas tree. And what is it asking? So it's saying that what is the fewest number of seconds that must elapse for the robots to display the Easter egg? Fascinating. Interesting. So what we are saying is that we will run this simulation. An interesting thing is in my approach for the part 1, I followed an object-oriented programming system for some reason, and I created a class called simulation that was there. And I was not maintaining a 2D grid, so I just maintained an array with the robot objects and where robots had its position. But I created a message called print grid, which is just iterating through all the robots that are there. And then they are just printing them on the grid for me to see. And it seems like this question is saying that we have an Easter egg where this print grid, after some n seconds or iteration, will start to look like a Christmas tree. And there is no image given, like what does a Christmas tree mean here. So I can only assume that it is one of those classic examples where I think order must emerge from chaos. And how do I find it? So This is interesting. I have some ideas, but I think now is a good time for you to pause and think as well that building on your first solution, can you think of a way that you can find out exactly when do you see a picture of a Christmas tree? And of course, since we are dealing with like a grid, which is not too big, it's 101 into 103. I'm assuming because we don't see any changes there. It is basically like a 100 by 100 pixel image where assuming that you are denoting each robot with something, maybe a star or maybe a hash pound, uh, at some n seconds, I think there will be one grid iteration or a frame where it should look like a Christmas tree. So that's the problem. So why don't you pause and think, and once you come back, let's discuss some theories on how we can find that. And yeah, welcome back. So let's talk about some of the approach. Honestly, I don't have a direct answer here, and I think this is like one of the last parts where we will have to rely on retro. But let me walk you through like how my brain is thinking about this problem. So what I can think is that from T0 to Tn, we will have a grid generation or a grid frame which will represent like something, and in middle like something like a Christmas tree, however it looks, should appear, and then it should go back to being like all random or something. Now what we have to do is we have to write some code or some method to find this image and find the value of n at which it is happening. So since this is a 100 by 100 image frame, what I'm thinking is that if I can overload my print grid method, so like obviously my first approach to solving everything is brute force, and that's exactly how you should also think, because then it allows you to build on top of it and optimize something. And even before brute force, I think of solving something manually, because once you know how to solve it manually, you can convert it into an algorithm and then write some code for that. So thinking about this problem, like I think if we put this here, what I am thinking is, and it also says that it will arrange them in the picture of this, and then it will go into this and fewest number of seconds. So looking at our examples, which is here, I think where we are doing some velocities, I have a theory that if you keep traversing, each robot has a very fixed path, right? Like if I look at the first one, which is starting from 0,4 and then moving in a direction, I have a feeling that eventually after some pattern, it probably can go back to the same position that it started with, basically the init position, which means that it should have like some kind of a cycle to it. And if one robot has a cycle, probably other robots will also have some kind of cycles here. But that does not help us really, because each robot will have a different cycle where, let's say, a robot 1 starts repeating it after 10 iterations. A robot 2 might repeat itself after 20 iterations. But there might be something here. Let me park it for now. Let's come back here. So in terms of brute forcing and thinking manually, what I'm thinking is that in very simple words, we can maintain the grid, and eventually, do you think like this grid will also have a cycle? Maybe, maybe not. It can't be irrational forever because these velocities are fixed and we are not moving them. So what I'm thinking is that maybe we can start with a number and try to see and print like these, print or store these grids somewhere for the first. And it was fairly fast to solve the part 1. So maybe we can save like first 1,000 grid. And I'm thinking, because it's a visual representation and humans are really good at finding pattern, we can just print it out and then just look at them. But the problem is if the answer is not in first 1,000, because it can be fairly large number, then it will take a lot of time. But I think that is first thing I'm going to try to do. I'm going to print some frames And I'm going to see if I can see like a pattern. And why 1000? I think even we can go 10,000. But problem is scanning through 10,000 grids is going to be a little difficult. So I think let's use our programming brain and think about something else. So now when it says that it forms an image, and considering we have a 101 by 103 grid, which is almost like a square off by 1 pixel, it can form anywhere, but a Christmas tree, how I understand, has always been, I don't know, it can be in this shape, it can be in this shape, it can be in this shape. And the interesting thing is Advent of Code follows like different input sets. I think I mentioned this in some video as well. It may very well be that I think everyone will have a different shape. But one thing that remains common if you look at some of these drawings is that you will have some continuous straight lines, right? To form an image, let's talk about what is an image. And in a traditional sense, of course, an image is like a collection of some pixels that are arranged in an order, which allows us to see a pattern. And usually this happens at an RGB, but here assuming that we are at a monochromatic image where we just have a bit that something is present and something is not present. In pattern, we can see that it should have some connected straight lines. So, how many? Minimum of 2, 3, 4. I think what I can do is building on top of this approach where I'm printing the grids. I think one enhancement that we can make is that we can check that whenever we have a TX grid, check if it's a lot of hit and trial, but I'm just speaking out of something, that if 5 robots have either same X or same Y and are in a continuous position. So which means that whenever in our grid these robots will form like a line, we can take that and we can send that to print. And what this will do is this will allow and reduce the noise a lot, that instead of printing all of these random frames, we will only print frames when we see some kind of a pattern that starts to form. And I'm using the number 5 here initially because in my head it seems fair that 100 by 100 grid, at least like when you're drawing a picture or a tree, there should be at least 5 robots that will be in a straight line, vertical or horizontal. And now what I can do is I can print maybe 1,000 of patterns like this. And I have a feeling that we should be able to find them very well. And sparring more, I think I'm going to try this approach. I think one more thing that comes into my mind is that, again, going to the grid, when things are random, the positions will be very sparse, right? Like there will be a chaos. There is no order. But when you have a picture of a tree, I'm sure there may be some robots that are not participating in it, but does it say is that every robot participates? Most of the robots. So that is the interesting line to read here. So it says that the most of the robots should form a tree, which means that if we are able to calculate some kind of a checksum, like a random checksum, randomness checksum, I'm not a machine learning engineer, folks. So, but I do understand that there are ways to calculate like how sparse, like a sparse checksum of the grid we can look for, because this one will definitely be an outlier when that happens. So if we are able to find a way to check this like a sparse score, again, we can mention a threshold. Like here we mentioned a threshold of 5. We can mention a threshold that if the score is greater than 0.5, you just print the image and then I can see. Sadly, there is no direct way of having the exact result programmatically that I can think of, because we are not given how a Christmas tree looks like. If we were given how a Christmas tree looks like, or even a subset of it, it would have been very simple, because then all you need to do is that as you are going through generating these frames from T0 to 2n, tn, all you need to do is you need to just match it with your frame that is given to you for reference, and then you have your answer. And yeah, I think with that we have three approach. There is a brute force approach. There is a heuristics where we see like if five, I will start with 5 and then maybe I will use the table doubling divide and conquer. If I don't see anything, I will make it 10. If I see nothing, it means it is somewhere in between. So I'll try with 7, 6. And then I think I should probably find answer in first few hundred frames. And then I'm going to try the other approach where I'm saying that I will try to see if I can calculate a score and then find an outlier. I think this might be very interesting because remember, if every robot is cyclical, the whole grid will also be cyclical after some iterations and can be in millions. And the tree will repeat itself because here another thing to look here is that it says that what is the fewest number of seconds that must elapse for the robots to display the Easter egg. So I'm trying to read between the lines. But yeah, with that, I think I'm going to go and write some code. And I would recommend you to also try that. And this is a very fun problem where the scope of the problem is not very clear. And I think I have not checked. I'm going to write some code and then check, but I'm sure like people would have done like really creative solutions here. So yeah, I'll go back and write some code and I'll see you in few minutes or few hours. I don't know, but let's see that. Hey folks, welcome back. And as you can see, we found the answer for a very abstract part 2, but we have received another gold star. And with that, finally, I have caught up with all 14 days. And the next problem will be back in 1 hour and 39 minutes. But so thankfully, both the approaches that were discussed actually worked. So what I did is I first initially just did a complete brute force and I generated the first 1,000 frames and I did not get the answer. So then I was like, okay, let's generate 10,000 frames. And if I still don't get the answer, I will move to the other one. And I got 10,000 frames and then it was just bunch of scattered things. But I saw like sometimes the robots will come close and form maybe a line or something. So I definitely knew our second approach is going to work. But then I was just going through all of that and I just saw something that resembled a tree. So I have this huge 32-inch 4K monitor and since I'm coding on Windows subsystem for Linux, I just mounted the folder and opened it in Windows Explorer and selected view as icons. And there it was, a tree staring back at me in its full glory of a 100 by 100 pixel image. But that was like a very high number. So I input that and that was not the case. So which meant like there was a tree before that I missed. So I just thought about like, does the robots coming together on a pixel, and since I exported them as a PNG using the pillow library in Python, I thought, let's see if I arrange them with size, what happens. And lo and behold, as soon as I arranged them with the size, all my tree images just came on top as they were lowest in size. Because somehow I think how PNG operates when it creates a file, the algorithm behind rendering, it counts for a smaller size of an image when the black pixels are closer than the white pixels, and when they are more sparse, the size was bigger. I'm going to probably read about it and will probably insert like a couple of screenshots here for you to see what I mean. And I will also maybe link a couple of resources around my hypothesis about PNG algorithm to encode a file and then keep the pixels together, resulting in a smaller size. But then I wanted to make it a little bit more optimized because 10,000 frames and going them, and this was like a fluke. So I wanted to see if this approach of finding where where everything, some of the robots co-locate with some kind of an alignment threshold works or not. And what I did is I initially said like I want all the robots, 5 robots, all the images where 5 robots are in a line either horizontal or vertical, and then just print them. And I asked it to print check for first 10,000 frames because I knew my answer is somewhere there, like I think from the part 1. And this worked really well. I did get some garbage data, as you can see in the screenshot here, but in just one single view, I could see all my trees that exist in like first 10,000 frames. And from there, it was as simple as just taking the answer, putting it in puzzle, and we were able to solve that. Sadly, I did not get enough time to check for the third approach where we can co-locate, we can do some kind of a checksum to calculate a score and then calculate based on that. But interestingly, I looked at the subreddit and how people are doing it, and my mind was blown. Of course, there were few people like me who were doing it by the eye, but I found some people who did like a whole analysis on the each grid and then tried to calculate an outlier. And I will link some of the posts here. You should definitely check them out. And I will also put some of the links in description below. And I think that is what is most beautiful about the part two of the problem. It was super ambiguous that you just have to find a Christmas tree. And I think, as I said before, I think the order just emerged from the chaos. So I think this one here, this was actually true today. And I really had fun, although some people did not like it. But yeah, with that, we are at the end of our day 14. And if you like this video, please subscribe and share it with your friends. And if you haven't seen my other last day 13 videos, please check them out. I am sure you will have fun and you will learn a thing or two. But with that, we are at the end, and I will see you in the next video. Bye-bye.